My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. So, hope you are well and safe from Corona pandemic. As we know that we are staying in a Corona pandemic situation, so it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 204th international physics webinar. Today it's our 205th international physics webinar. We have with us here today Dr. Robert I. Hynes, sir, Professor of Physics, Department of Physics and Astronomy, Louisiana State University, Louisiana, USA, and he has already connected with us. So I'd like to welcome our speakers. Good morning, and good evening to hear. So, yeah, thanks for accepting our invitation, sir. And we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. Dear student and viewers, you can also join with us by using this link, and you can also ask question by commenting. So I think you have already come to know the title of this today's International Physics webinar. Title is the Outburst of the Galactic Black Holes. Very exciting title, and I think you will enjoy this session. And our speaker is Dr. Robert I. Hynes, sir, Professor of Physics, Department of Physics and Astronomy, Louisiana State University, USA. So sir, it's your time. You can start your session. I think you will also enjoy our session. And I'm happy that this is your first online session, and you are giving us time for the first time. So I'm very lucky and grateful actually that you gave us time. And it's my honor and privilege to host you in our International Physics webinar, sir. Thanks again, sir.
Okay, ready for me to go?
Start.
Okay.
Yeah.
So, yeah, thank you. It's an honor to be here. And as you said, it's my first time trying to do a international colloquium type thing. So I hope that this will go okay, and I hope the connection will work okay. So I'm going to be talking about the outbursts of galactic black holes. But I'm actually going to start off, this is a picture of what I'm actually going to talk about, but I'm going to start off with something completely different. Dinosaurs, because everyone loves dinosaurs. So this is probably a picture of something many of you have seen before, a picture of bones of a dinosaur assembled into a complete skeleton. And that's a fascinating story in its own right. I'm not going to devote too much time to it. But scientists found these bones. They were able to figure out how to connect them up, which ones came from which kind of dinosaur. And they were able to build these skeletons. And then people went on to try and figure out from these fossils, what did the original thing look like when it walked around? And we had various versions of what these dinosaurs might have looked like. Here is one from my daughter's collection. This is one rendition of what a raptor dinosaur might have looked like, a velociraptor. And it's probably a familiar image. If you have better technology, you create images like this. These are from probably the famous movies, Jurassic Park movies, Jurassic World. And you have these classic images of what these dinosaurs might have looked like. Scary things, these scaled lizard things, reptile things. But it turns out that that may have missed something completely major about these things. And that the fossil record didn't preserve all the information we needed to reconstruct what they actually looked like. And so now we kind of think that instead of these lean, mean death machines that were depicted in the movies, what these raptors may have actually looked like is more like killer chickens, that they had feathers. And frankly, they look kind of ridiculous. Still deadly, but definitely not the image that many of us grew up with of dinosaurs. Why am I talking about this? Because this was an attempt, this version and then this version, are both attempts to try and reconstruct what these things look like based on fossils, based on digging up the remains, based on very indirect evidence. And when we talk about outbursts of black holes, there's different kinds of black holes. And sometimes we're also working from very indirect fossil evidence. So the poster that Dr. Das put together kindly for this talk drew on a press release, which I have to say had nothing to do with me. And so I'm not taking any credit for this, but I thought I would take that and run with it and talk a bit about that. So this was based on a story about the black hole at the center of our own galaxy, what is usually known as Sagittarius A star. This is a 4 million solar mass, 4 million times the mass of the sun, black hole sitting at the very exact center of the Milky Way galaxy. And at the top right is an artist's picture of what this might look like, or what one of these supermassive black holes might look like when you have an accretion disk of gas spiraling in towards the black hole. The actual press story was about things a lot further away. And so the bottom left picture shows fairly small our Milky Way galaxy labeled there. And it also shows two of our satellite galaxies, the Large Magellanic Cloud LMC and the Small Magellanic Cloud SMC. Our Milky Way has, we think, at least 60 of these satellite galaxies, but these are the two by far the most obvious ones. And you can actually see them in the naked eye from the southern hemisphere. We also know that as these galaxies orbit around the Milky Way, tidal forces have drawn out some material from them into arcs around the Milky Way. And so you have these Magellanic streams stretching around the galaxy. And what Dr. Hawthorne and collaborators found is that part of this Magellanic stream is excited and is glowing in emission lines. And they looked at various explanations, and the best they could come up with is that this Magellanic stream was lit up by a giant outburst of a black hole at the center of our own galaxy about 2 million years ago. Give or take a million. It's not very precise. This is an example of using fossil evidence for glow from this Magellanic stream to reconstruct an outburst of a Milky Way black hole millions of years ago. We believe it happened, but it's hard to really say much more than that. And so this is a case where fossil evidence of this outburst gave us a very incomplete picture. And so it would be so much better if you could actually look and watch these outbursts happening. And there's several ways of doing this. One is to look at other galaxies where the light from an outburst is reaching us right now, and we can see what happens in a supermassive black hole, kind of like ours. But the problem there is still that these outbursts in supermassive black holes happen really, really, really slowly. And so it's hard to really see how things develop and what effects lead to what. It's hard to see a cause and effect relationship. But it turns out that there's a fairly simple scaling between the duration of these outbursts and the time scale where things happen and the mass of a black hole. The bigger the black hole is, the larger its event horizon is, the larger everything around it is, and the slower everything happens. And so if you go to smaller black holes, everything happens faster. And that's what I'm going to be talking about in this talk, is what happens when you go down to black holes more like 5 to 10 times the mass of the sun. It turns out when you go down there, you then have outbursts that last less than a year, and you have events that we can watch on everywhere down to millisecond timescales. And so it's very accessible for modern astronomers' lives, and modern instrumentation. And that is the kind of things that I actually work on. So what I'm going to start off then is telling you a bit about these galactic black holes. What I'm going to focus a good chunk of the talk on is relativistic jets from these black holes. And actually that picture of Milky Way, there's these things called Fermi bubbles, which I'm going to come back to, that may also be tied into relativistic jets. We'll see. If I have time, I'm going to talk about the masses of black holes. That's one thing I may drop if depending on how fast I'm going. And then finally, to try and bring in a bit of my own research, I'm going to talk about the outbursts of one of these black holes as a case study. This happened in 2015 of a famous black hole called V404 Cygni, the 404th variable star discovered in the constellation Cygnus. So what are these things? Let me start off by talking about X-ray sources in the sky. We discovered about 60 years ago that there are X-rays coming from outside the solar system. Until then, the only X-ray source that we knew about was the sun. And that's for good reasons. If this is from a table from NASA, if you look at different objects in the X-ray sky listed at the left, you can measure their X-ray flux, their X-ray brightness. These are in units measured relative to an astronomical source called the Crab Nebula. That we now know, whole different seminar, is not actually a constant source of light, but it's close enough to give you a good measure of the relative brightness of things. And barring one unusual event that happened in 2004, by far, by a factor of about 110 to 100,000, the brightest thing in the X-ray sky is the sun. And until 1962, that was the only thing that we knew. Since then, we've discovered there's a host of other things. And we think that if we'd had X-ray telescopes before about 1900, that the black hole at the center of our galaxy, Sagittarius A star, would have made this list of the brightest things in the sky. Right now, it doesn't come close. It's really, really faint. But we think that even a few hundred years ago, it was pretty bright. That little anomaly, soft gamma ray repeater 1806-20, is, again, could be a whole different talk in itself. This was an event that happened in December of 2004, just after Christmas, and it was staggering. It lasted seconds, a few hundred seconds, and there was a single really bright flash, and then it just kind of oscillated and faded away. At the peak, this was comparable in brightness to the sun in X-rays, even though it is on the other side of a galaxy 15,000 parsecs away, about 50,000 light years. And it was so bright that it actually measurably ionized the Earth's atmosphere. We could detect its effect on our atmosphere. So that was kind of a weird thing on its own. We now believe that that's a highly magnetic neutron star and is not actually a black hole. Barring that, every other X-ray source that we've seen has been many orders of magnitude fainter than the sun. So what are a lot of these other things that are mentioned? Well, it turns out many of these things have dates by them because they're rare events. They're not things which are bright all the time. SCO-X1 down here is a one exception. Most of these things are transient events. And a representative example, the famous example, is something called A0620-00. What this refers to is what discovered it, in this case, a satellite called Ariel 5. That's where the A came from. And then the numbers are coordinates on the sky. It's actually a very useful system, but it's not a particularly friendly naming convention. It's just coordinates. So this was discovered in 1975. People then got curious and went back and looked at old photographic plates and found that actually it had an outburst in 1917 that nobody had noticed. And at the time in 1975, this was the brightest extrasolar X-ray source that we had seen, and remained that way for a long time until 2004. And certainly when I started giving these talks, I could claim that it was the brightest extrasolar X-ray source. We've since been trumped, but for a while we had that. It had an outburst that lasted about 200 days. So these plots are a little busy. So let me explain a bit of what is going on. The x-axis down here is time measured in days. It's a convention called Julian dates, which is just a kind of decimal date since a fixed point in time. This range is about 200 days. Don't worry too much about the 0 point. It's somewhere around 4000 BCE. The y-axis on the left-hand plot is a logarithmic scale of X-ray intensity. And you can see it rapidly rose by several orders of magnitude and then gradually faded. It's a straight line in a logarithmic plot, so that corresponds to an exponential decay. It exponentially decayed in brightness over about 200 days. The right-hand plot is optical magnitudes, that is basically the same thing. It is a logarithmic measure of optical brightness. For historical reasons, optical astronomers use this magnitude system. It's a logarithmic scale, and smaller numbers are brighter, but it basically corresponds to a logarithmic scale. This is about a factor of about 1,000 from 18 to 12. And again, we saw the same thing. It rapidly rose in optical brightness and faded away exponentially. And so this became a prototype for a class of X-ray transients. And many of these bright things are X-ray transients. And it turned out many of them, we now know with hindsight, actually contain black holes. The ones I've highlighted in yellow and green are black hole binaries, where we have these black hole outbursts, galactic black hole outbursts that I'm talking about. So that accounts for 4 of these brightest objects in the sky. And it turns out that Centaurus X4 is very similar, involving a neutron star, and Scorpius X1 is also very similar, involving a persistently bright neutron star. So those account for many of the brightest X-ray sources in the sky. The one I'm going to highlight is V404 Cygni. Again, 404th variable star discovered in Cygnus. And I'll be talking more about this later. This was discovered in 1989 as originally it was classed as a classical nova, a new star, Nova Cygni 1938. It then went into outburst again in 1956 and 1979. And 1989 was the one where we finally discovered it with X-ray telescopes and discovered this is not a nova. This is something very different. And this turned out to be one of the strongest cases for a galactic black hole. And in this case, the light curve shown is kind of similar, but a bit shorter. It lasts for a few months, and it's much, much more noisy. And we'll look at a much better rendition of what a modern outburst looks like. So this went off in 1956, 1979, 1989, every 10 to 20 years. And so by 2012, it was overdue for an outburst. And many of us had as our kind of dream scenario, one day this is going to go into an outburst again. And there's so many exciting things that we can do with it. And we got excited. I'll come back to what actually happened. It was, in some ways, every bit as exciting, and in some ways, kind of a missed opportunity. But we'll talk about that. So what are these things? We believe these are binary stars, where one of the stars, basically a point prick that you can't see in this image, is a black hole, probably somewhere around typically 30 kilometers in radius, so kind of like size of a large city. And the other star is a normal star, probably low, typically lower mass than the sun, a red dwarf star, orange dwarf star, maybe a little larger. They orbit in periods of anywhere from a few hours for the star to orbit the black hole up to a few days. The star is close enough to the black hole that actually the surface of the star is marginally bound to the star, and some material can overflow into the potential well of a black hole. That's called Roche lobe overflow. The material overflows through the closest point as an accretion stream. Because it has angular momentum, it cannot fall straight onto the black hole. And so it comes in a bit of an angle and starts colliding with itself and then forms this disk. Material in the disk then gradually spirals in as angular momentum is removed by viscosity within this accretion disk. And eventually it accretes onto the black hole. Large amounts of gravitational potential energy is converted to heat, and the inner disk is heated up so bright that it glows in X-rays. And other things go on. Somehow these things produce relativistic jets. We're still not exactly sure of the process. That's one of the goals of trying to figure out how that works. And sometimes they produce anywhere up to very strong winds from the disk as well that may actually result in carrying away a lot of the mass before it ever accretes onto the black hole. Generically, these things are called low mass X-ray binaries. X-ray binaries because they're binary stars that produce X-rays. Low mass because this companion star is a low mass star, typically the sun's mass or less. There is another class of high mass X-ray binaries with supergiant type stars that I'm not going to talk about. So that's a cartoon view, and keep it in mind as we talk about what goes on. These are exciting objects. We can view them with essentially almost every kind of telescope we have. They're detectable right across the electromagnetic spectrum. In the radio, we typically detect the jets and maybe outflows from the disk, but principally what we see is the jets, the relativistic jets. As you go into the infrared, you start to see the companion stars. You may see also strong radiation from the jets. This work can be done from the ground or from the space, and we're particularly excited about doing this with the James Webb Space Telescope. Moving into the optical, the accretion disks start to become more dominant. Again, this can be done from the ground. As you go into the ultraviolet with things like Hubble Space Telescope and SWIFT, you have to move to space, and typically you are very dominated by the accretion disk. As you go to the X-rays, you get fantastic time resolution getting down to milliseconds, although we really are kind of getting into that millisecond regime in the optical, and hopefully soon, and to some degree the infrared as well. Down there, we are looking at the very closest accretion disk, close to the event horizon of a black hole. And we are looking at very hot gas, what's called coronal gas, that is in clouds probably above the accretion disk. This is done by an array of X-ray satellites. And going from hard X-rays, things kind of smoothly transition into gamma rays, which is dominated by hot gas, and again, a number of gamma ray space telescopes. So this is truly multi-wavelength astronomy. At this point, what it is not, I'm sad to say, is really multi-messenger astronomy, because it is still very photon-based. These are not gravitational wave sources, and we've yet to detect any neutrinos and probably don't expect neutrinos anytime soon. They may, in some cases, be cosmic ray sources. And so we may squeak into multi-messenger there. Okay, so that's a kind of bit of an overview of what these things are. Let me talk a bit more about jets, because that plays a big role in what's coming up. So I'm actually going to start off not talking about the galactic black holes. I'm going to talk about supermassive black holes. Some of the first radio sources that we discovered were supermassive black holes. And any time things have a name that's like a constellation followed by a letter, like Cygnus A, or we earlier on mentioned Sagittarius A star, those are among the very first handful of radio sources discovered in the sky, the brightest radio sources in the sky. Cygnus A is the brightest radio source in the constellation Cygnus. Sagittarius A is the brightest radio source in the constellation Sagittarius. Sagittarius A star is part of the whole Sagittarius A complex emission. So this Cygnus A, when it was first discovered, was just big bright thing in the direction Cygnus. But with better radio telescopes, we saw it was this truly crazy thing. And we now know this is a 2.5 billion solar mass black hole. So about 1,000 times bigger than the black hole at the center of our own galaxy. The black hole is down at the center of this little dot in this radio image. It produces relativistic jets that blast out and blow up these radio lobes. And as a sense of scale, the Milky Way would be kind of a little fuzz around that central dot. These lobes are much, much, much bigger than the size of the Milky Way. I believe the whole thing is about the scale of the Milky Way and the Andromeda Galaxy combined. And if you look in X-rays, what you can see is these jets come out, and then we see hotspots that are labeled with these letters, where the jets collide with the edges of these bubbles, and in some cases they even ricochet and bounce around inside these bubbles. And as they do that, they deposit energy in these bubbles. There are clouds of charged particles. And then those clouds of charged particles are what give rise to these radio lobes. The energetic electrons then radiate by synchrotron emission. They spiral around magnetic fields and produce those large radio lobes. Oops. In the case of a Milky Way, we have much weaker evidence that the same thing is going on. So going down a factor of about 1,000, we discovered about 10 years ago that in gamma rays, you can see, top left picture, these very faint gamma ray lobes to either side of the central black hole. And artist's impression is a lot better. You can see there's this kind of diffuse gamma ray emission and then X-rays from around the edges. Probably the leading theory is that these are radio lobes produced by jets from the central black hole. That's not the only possible explanation. They could also be related to ejecta from a burst of star formation, but I think most people favor associating this actually, again, with a burst of activity of our central black hole a few million years ago. These are probably a few million years old. So those are on very big scales. If you go down to galactic black holes, like I said at the beginning, everything happens faster. And so in the 1990s, there was a couple of cool discoveries from two of these galactic black holes, where we saw that these relativistic jets were spatially resolved, but also that they were expanding in real time over days, weeks. You could actually watch blobs of gas, plasma in these jets expanding outwards, and you could trace their motion, see how fast they were moving, and so on. And so this gave rise to a couple of nature covers, including the somewhat hyped superluminal motion in our galaxy. Because if you track how fast these things seem to be moving across the sky and how far away they are, what you infer is that actually these jets are expanding faster than the speed of light, which of course we know would break physics and is not actually happening. This is basically just an illusion. And what this superluminal motion is that the jets are actually not just moving across the sky, they're actually moving towards us. One of the jets is coming towards us, one is receding. And as it's coming towards us, successive times as it gets closer have less of a distance to travel. And so emission from this B point in the jet has a shorter distance to travel than the A point in the jet, so it leaves with a head start. And it seems to arrive earlier than it should do and gives the impression it moved faster than the speed of light. But actually, it's an illusion. These jets are moving very close to the speed of light. They are truly relativistic, but they are still moving a little bit less than the speed of light. Things like Cygnus A are a group of what are called active galaxies. The brightest of these are known as quasars. And so when you go down a factor of 1 million or 1 billion in scale, you get things which were then dubbed microquasars. And there was a lot of hype about these as microquasars, and it's valid because it turns out a lot of the physics of how these jets work is common across this factor of 10 to the 9 in magnitudes. A lot of the physics that you learn by studying one class of relativistic jet sources from black holes can be applied to the other one, in spite of a difference in scale of a factor of 1 billion. And so they are very useful as tools to figure out how relativistic jet launching works. And so one of the themes of this talk is that you can learn about the jets and the mechanisms of jets in supermassive black holes by studying these galactic black hole binary outbursts. And the great thing is that they happen on timescales of days to weeks, like you can see on this cover, instead of years or more that you would need to study the same kind of thing in a supermassive black hole. What we think is actually going on loosely is that you have an accretion disk. As the accretion disk gets very close to the black hole, you are winding up whatever magnetic fields are in the accretion disk. And generically, we expect there to be magnetic fields in the accretion disk. It's very hard not to be. There are instabilities which lead to a kind of growth of magnetic fields. There is an instability, kind of like a dynamo, which leads to building up magnetic fields within the disk. These then get wound up by differential rotation, and you end up with these tangled kind of spiral patterns. And we think that that tangled spiral pattern is what gives rise to the jet, that this effectively collimates relativistic particles and forces them out into a narrow beam and plays a large role in their acceleration. And that close to the black hole, there is a region where the relativistic plasma is accelerated and then collimated into these narrow jets. Exactly how it works is what we're still trying to figure out. And there's basically two competing mechanisms. One is a purely magnetohydrodynamic process, which is where the jet is launched by the inner part of the accretion disk. The other more exotic one is that maybe the black hole itself is involved and the magnetic fields thread through the event horizon of a black hole, and that the jet is actually powered by extracting some of the rotational energy of the jet. And we're still trying to figure out which of those processes is dominant, and maybe they both play a role. Okay, let me say a little bit about masses of black holes. I think I'm okay on time to do this. So this is the only equations that are going to feature in the talk. You can figure out a lot about the orbits of binaries using some very basic math. And the math actually goes back to Johannes Kepler figuring out how the solar system works. He figured out some laws of planetary motion within the solar system, Kepler's laws. And then we can take Newtonian mechanics and interpret what those laws actually mean. And this is what you actually get. This basically comes from relating Newtonian gravity, that's where the G's and M's come from, to circular motion and the circumference of the orbit. And you get what's called Kepler's third law, which relates the mass of the compact object, M1, the mass of a companion, M2, to the binary separation, A, and the orbital period, P. You can then do some math on that, which I'm going to skip over, and relate that to orbital velocities. And it turns out you can use those orbital velocities to then figure out what the mass of the black hole actually is. And what you get out is something that we call a mass function. And the mass function, this f of m, we can represent in two different ways. The first one is based on purely observed quantities of a binary. The second one is based on physical quantities. The observed quantities we get from something called a radial velocity curve. The idea of this is that as the secondary star orbits around the center of mass of a binary, sometimes we see it blue shifted when it's approaching towards us by Doppler effects. Sometimes we see it red shifted. We can measure that velocity by looking at shifts in the velocity of absorption lines in the spectrum of the secondary star. As we look at how those shifts change over time, we can plot a radial velocity curve. And this is an example from 1986. This is actually the first of these objects, A0620. And this is the first one for which we got a good mass. What we see is over the orbital period of this object, of about 8 hours, the x-axis is is time in hours, we see the radial velocity go from maximum blue shift to maximum red shift, and then it would go back to maximum blue shift again. We can measure the period of that, P, directly from the time between troughs. We can measure the amplitude, and usually we measure the semi-amplitude, K, the half the full amplitude. And if you take K and P, then K cubed P together with a gravitational constant and pi gives us this mass function. So this thing is directly measured from spectral measurements. What makes this interesting is that you can also express this mass function in terms of the mass of a black hole, the orbital inclination, the tilt of the orbit with respect to our line of sight, and the ratio of masses. This Q is the ratio of the mass of the donor star to the mass of a black hole. It's typically much less than 1 in these systems. The reason why this is interesting is because the sign is always less than or equal to 1. Q is a positive number, so 1 plus Q is always greater than 1. So this mass function has to be, mathematically, has to be smaller than the mass of a black hole. So the measured mass function gives a strict lower limit to the mass of a black hole. In the case of A0620, that came out to 3 plus or minus 0.16 solar masses. And so that very strongly pointed towards this being a black hole. This is too large to be a neutron star. To give you another example, in the case of Cygnus X1, the other case study that I'm talking about, we get an exquisite radial velocity curve. This is from the 90s. And very precisely measured orbital period, 6.47 days. This is quite a long period. And a radial velocity semi-amplitude measured to better than 1%, a bit better than 0.5% actually. And so we get a very precise mass function, which is actually much too big to be a neutron star. And so this was a very strong case for being a black hole. We now have about 20 to 30 of these stellar mass black hole measurements. And we live in a very exciting era post-2015, where we can start comparing these galactic black holes, what are sometimes called the electromagnetic black holes, EM black holes, with the rapidly growing plot of LIGO black holes, gravitational wave black holes. This plot didn't exist before 2015. And since 2015, I'm sad to admit the number of gravitationally wave black holes, discovered black holes, is now dwarfing the number of our poor galactic black holes. And we can start to look at patterns. The first thing we notice is that the gravitational wave black holes shown in blue have higher masses, the y-axis is mass, than typically are seen among the electromagnetic black holes shown in purple. They overlap. There certainly are gravitational wave black holes of comparable masses, but typically the things we're finding are higher masses. That may not mean much. The masses of a black holes that merge and produce gravitational waves strongly affects the strength of the signal, and so these high mass black holes can be seen much, much further away. That means we can see a larger volume, and so there's a very strong selection effect, which means that these statistics are biased towards the high mass black holes. And so some of this may be a selection effect. The blue black holes do exist at lower masses, they're just harder to find. There may also be physical changes, that some of these high mass merging black holes are fundamentally coming from a different astrophysical population. And we're still figuring out where they come from at this point. The other big difference, which is much harder to explain as a selection effect, is that when you compare these electromagnetic black holes to the equivalent electromagnetic neutron stars shown in yellow, there's quite a strong mass gap. From about 3 to 5 solar masses, we really don't see anything. And it's possible to put things in that gap with neutron star mergers, and we've seen that with LIGO events. There's a handful. But generally, that seems to be lightly populated. And so that is probably telling us something about the stellar deaths that produce black holes and neutron stars, that you either produce the low mass objects, neutron stars, or the high mass objects, black holes, and almost never anything in between. Whether we really produce things in between is still something we're trying to figure out. So that's a bit about black hole masses. The final thing I want to talk about with my last, 15 minutes or so, 20 minutes, is V404 Cygni. So this is a case study in what one of these black hole outbursts actually does. And this is a chance to bring in work that I've actually done myself. So I said that by 2012, this outburst was overdue. In 2015, finally it happened. It was very, very exciting to those of us in the community. This is the original announcement where it was discovered by the Neil Gehrels Swift Observatory. And close to, let's see, 6 years ago, almost to the day, they discovered at 1855 hours that, announced at 1855, that there was a detection about 24 minutes earlier. So pretty good turnaround. The whole world was told within 24 minutes that this thing had gone and this black hole was going into outburst. And pretty quickly, they went from a rough position down to positioning it to better than an arc second. That's a very small area in the sky, and gave us a very strong confidence that these gamma rays were in fact coming from V404 Cygni. And so at that point, all of the community that works on these things went into overdrive. And this is borrowing a cartoon from Farside. It is also shamelessly borrowing from talks that were given by my advisor like 25 years ago, where Carol Haswell, she used to show this slide of what happens when black holes go into outbursts. And it's still true. All day long, a tough gang of astrophysicists would monopolize the telescope and intimidate other researchers. And this still happens. We go into action, we try and take over the world's telescopes. I was particularly involved in one collaboration. These are my collaborators. So Rob Robinson happened to be on the 2.1 meter telescope in McDonald Observatory in Texas. Poshak Gandhi and collaborators in Southampton were able to get time on the William Herschel telescope in the Canary Islands. Donald Tundrup, who doesn't even work on these things, was on the MDM, one of the MDM telescopes in Arizona, and was persuaded by some of his collaborators who do work on this, particularly Mark Wagner, that, hey, this would be a cool thing to observe. And Cindy Froning got some time on the Las Cumbres Observatory. And we eventually somehow mashed this data together into a paper. There was also, and this was part of a larger collaboration that was put together by Christian Kniga. Huge props to him. He's at University of Southampton. He thought it would be a great idea, instead of us all competing to try and race to get publications out, let's all try and work together and produce some joint papers. That was largely how this came together. And that also led to the other group of papers that I'm going to talk about by Poshak Gandhi, focusing on the highest time resolution down to millisecond timescales. So what we saw was, on the one hand, really exciting. This plot, again, let me unpack it a bit. The x-axis is in days. Basically, this spanned June, and not much more than June. The y-axis, the bottom two plots are X-ray count rates, so that's a linear scale measured in kind of very hard X-rays on the bottom and softer X-rays in the middle. The y-axis is these magnitude things. Again, that is a logarithmic scale of optical brightness. It's a conventional thing for optical astronomers. This is from our paper, and so this is the data that we got from a combination of, this is McDonald Observatory data, MDM Observatory data, William Herschel data, and then the dots are Las Cumbres. Where I said earlier that this was an anticlimax was, we all got so excited for this thing, and within 2 weeks, actually 11 days, it was basically over. So much so that Christian Kniga, who had got director's discretionary time on the Hubble Space Telescope, never actually got any data, because the outburst was over before they could get Hubble Space Telescope onto it. It was a very short event. Basically, what we think happened was all this violent flaring and outbursting, a lot more than many of these objects, a lot more violent, essentially blew the accretion disk apart. And we saw evidence of huge ejections of large amounts of a disk just being blown off into space. It is among the most violent outbursts of a galactic black hole that we have seen. And the theme, as we look at shorter and shorter timescales, is that things get just keep remaining like this. There are flares down to timescales of milliseconds. It never really gets perfectly smooth. So let's look in a little more detail. This is from one of our nights on the McDonald Observatory. To try and make it a little more accessible to physicists now, this is a purely linear flux scale. I've dropped the magnitudes. Again, bottom plot is hard X-rays. Middle plot is softer but still hardish X-rays. And top plot is optical fluxes now. This is just energy per second per unit area. The time scale down here is 2.86 to 2.94. So that is about 1/10 of a day. So about 2 to 3 hours. And what you can see in the optical is there's all sorts of things going on. And that coincides with flares in the X-rays. There's 3 major kind of events going on in the X-rays. And within those events, there's all sorts of substructure, which we'll expand on. Within the optical, there's a lot of weird stuff going on. It's varying over the course of 3 hours. It's varying from about 15 of these flux units up to about 120. So by about a factor of 10 in 3 hours. And even there, that doesn't begin to sample the timescales of what's really going on. What I'm going to highlight is 3 particular kind of behavior. There is this general kind of up and down, but there's also some distinctive things. The things I've labeled A is this very smooth, almost exponential decline. And there's other of these that we observed. So this is a kind of recurrent pattern that happens sometimes. Then period B, you see that the optical kind of goes from this fairly smooth trend to violently jaggy and then smooth again. And then C, there's these little kind of flashes in the optical that I have never seen before. And when I first saw this light curve, my reaction was, don't believe it. To actually give you a little bit of historical flavor, this whole thing happened just as I was about to go to a proposal review for Chandra X-ray Observatory. And it turned out when I was there, my whole panel, there was like 6 of us. Every one of us was involved in this camp, in these observations at some way in different projects on V404 Cygni. And so it was very hard to kind of focus on what we were supposed to be doing when we were all so excited about this. These data I got from Rob Robinson and was looking at in my hotel room after the meeting and trying to write astronomical telegrams about these from my hotel room. And when I first saw these fast flashes I've labeled C, I was like, that's not real. Something went wrong with the instrument. What on earth is going on? And then I saw some of the data from the MDM observatory from Don Turndrup, and they overlapped and saw the same thing. So this is real. These are from 2 different observatories in different states in the US, and we see these fast flashes. So I'll come back to those. So back to this picture. What could all of this stuff mean? You have a secondary star orbiting around a compact object, and you have an accretion disk. Traditionally, what we've tend to think is that a lot of the optical variability that you've seen there is caused when X-rays that you see down here light up the accretion disk, they light up the secondary star, and they produce thermal reprocessing. This is an idea originally developed for supermassive black holes, the active galactic nuclei, called reverberation mapping. And the idea is that the X-rays, some of the X-rays travel directly towards us, others go out, they heat up things like a secondary star, that gets hotter, it glows in the optical, it firmly reprocesses the X-rays back to black body-ish radiation in the ultraviolet and the optical. And we then see that. But because the reprocessed radiation involves a longer path, there is a path difference, and we see a delay on timescales comparable to the size of a binary in light seconds. In the case of V404 Cygni, it's a 6.5-day orbit, and so you expect lags from the accretion disk of up to about 80 seconds That is a path difference between direct and indirect radiation. The path differences from a secondary star would be even longer and would also depend on where the secondary star is in its orbit. And for a long time, up until about 20 years ago, this was thought to be the major mechanism for how you get optical variability in outbursts. Since then, this jet has become appreciated as being more and more important. And it is possible that some of this optical variability can actually come from synchrotron emission from these jets. And as you'll see, actually a lot of what we're seeing, we think may be synchrotron emission from the jets. So the first thing that's going on is these smooth declines. This is a close-up of one of these smooth declines, and you can now see the x-axis is now labeled in seconds. And so this decline is happening over a space of about 400 seconds, and actually keeps continuing out to about 1,000 seconds after it happens. The start of the decline, the dotted line, coincides with a dramatic drop in X-ray brightness, and there's a little bit of a blip in the optical just as it starts. We've seen things like this. In another black hole binary, again, one of these kind of coordinate-based telephone numbers, we see something similar. You see X-rays denoted by this black curve is oscillating, violently variable, and then suddenly drops into a dip. Then we saw that about 20 minutes after the X-ray dip, we saw first an infrared flare for red points, then we saw a radio flare in the blue points. And what we think happened there is that the inner part of the accretion disk became unstable and was ejected as blobs of plasma into the jet. As those blobs of plasma expanded, we first saw them glow as an infrared synchrotron flare and then as a radio synchrotron flare. And it's possible that something similar is happening. And indeed, there was very successful modeling of radio shown in the bottom plots and sub-millimeter, shorter wavelength, shown in the top plots. There's very successful modeling of light curves of these things in V404 Cygni by Alex Teterenko, using a model purely based on ejecting these blobs of plasma into the jets. So we know that these plasma ejections are going on. And so it's possible what happened here is the X-rays dropped because there was one of these plasma ejections, and it took a while to reform a disk. It took about 1,000 seconds to reform a disk. And during this time, we then saw the decaying optical emission from this plasma. The decaying timescale, hundreds up to thousands of seconds, is really a bit too long to just be the disk fading away. The timescales are too long. So that may be jet related. Then the next thing going on is, I really should finish up soon. I am close to finishing up. The next thing going on is that you have this rapid flaring, and weirdly, sometimes this rapid flaring cannot be there, then it can turn on, then it can turn off again. This whole plot is at 2,000 seconds. It doesn't really do justice. This is a close-up of about 250 seconds. And each one of these points, again, top plot is the optical flux. Each one of these points is 1 second. And so you can see that some of these flares are actually not even resolved with 1 second light curves. And some of them you go from like 30-something units up to 40 to 50 units in the space of 1 second and back up again. There's a significant change in the optical brightness in just a second. Remember, the accretion disk is like 80 light seconds across. If you tried to light up the accretion disk, it would smear it out. The different parts of the accretion disk would radiate with different delays. And so if you're seeing something happening in the space of a second, that implies that actually it happened from a region less than 1 light second across. That is much smaller than the accretion disk. Actually, if you go even faster, this is where Poshak Gandhi's work came in, you see that 1 second doesn't even do justice to it. This is a light curve. You can see all these fast flares superposed on the slower variations. And you can see that when you zoom this in, this bottom plot is now just 10 seconds across. These flares are actually more like 100 milliseconds, maybe even less. They are tiny, tiny things. And what he saw is if you compare these fast flares to the simultaneous X-rays, these fast 100 millisecond, 50 millisecond optical flares lag behind the X-rays. This is what's called a cross-correlation function. They lag behind by about 1/10 of a second. That tells you the region where the X-rays are coming from is something like 1/10 of a light second away from the region where the X-rays are coming from. And the best interpretation that we could come up with this is that these are coming from the relativistic jet. You have X-rays coming from the place where the jet is launched, the accretion disk. You have an acceleration and collimation zone, the ACZ, and then the optical comes from the base of the jet proper, which is about 1,000 Schwarzschild radii from a black hole. We think that by studying the fast flaring, these are events in the optical light, visible light, representing, in this case, up to a factor of 2 almost change in optical light from within 1,000 Schwarzschild radii of a black hole. The optical light is not just telling us about the huge accretion disk around the black hole. It is actually telling us about the region where the jet is formed, 1,000 Schwarzschild radii from a black hole. And so this is exciting because this can potentially tell us, watching in real time, how the jets are formed, and that can potentially in turn tell us about how the jets in supermassive black holes may be formed as well, because a lot of that jet collimation and launching physics is believed to be scale invariant for all black holes. My time is up, so I'm not going to talk any more about those big flares, except to say, hey, we don't really know what they are anyway. They last a few seconds. They're really big. What I will finish up on telling you about is what is coming up. So we're very excited that we were able to get time with some of the lucky groups who got time on the James Webb Space Telescope. Here's some pictures of it in the lab. Hopefully going to launch in October-ish. And we have time coming up to try and observe 2 of these black hole outbursts and try and study these jets in more detail in the mid-infrared. Because it turns out the optical is not a great place to study this. You can kind of see it, but really most of the excitement is in the mid-infrared, where James Webb is really, really optimized. And so we are very much hoping that it will launch successfully, very much hoping that we will actually get an outburst at the right time, and very much hoping we'll get some cool data showing us how jets are launched and how jet launching physics works. Maybe even telling us something about whether they are launched purely by the disk or whether they involve the spin of a black hole. And that is where I will finish up. So to give you a summary, many of the brightest X-ray sources that we see in the sky are actually galactic black hole binaries. And these are the objects that LIGO people call the electromagnetic black holes. They've given us most of what we knew, at least before LIGO, about the masses of stellar mass black holes. I've told you they undergo dramatic X-ray outbursts, and these happen fast, so we can study them in astronomers' lifetime and maybe even PhD lifetimes. They produce relativistic jets. And kind of surprisingly, for the last 20 years, these relativistic jets may actually be responsible for a lot of the optical variability that we have seen. And in the future, we hope that James Webb will give us a much better view of this optical variability. Thank you for your patience. Apologize, I've gone a little long, but I hope I have not gone excessively long. Thank you.
Thank you, sir, for your wonderful and exciting presentation, sir. So we have got few questions. So if you allow, we can start our discussion session.
Okay.
The first question is, what is the stream impact point?
Okay, so go way back. Let's see if I can find that plot. So secondary star is filling up its potential well, and it turns out that when you look at these gravitational potentials in 3 dimensions, there is a point called the inner Lagrangian point, or the L1 point, which is a saddle point between the potential well of the companion star and the gravitational potential well of a black hole. That is the easiest place for material to escape from a secondary star. And to some degree, it escapes just through thermal pressure, because some of the atoms are moving faster than the others, and so they can drift across into the potential well of a black hole. At that point, they have angular momentum, so they fall in a diagonal stream rather than straight towards a black hole, and that gives rise to this accretion stream. That would naturally form an orbit around the black hole, but once it completes an orbit, it will come back and collide with that stream. The stream will effectively collide with itself. When it does, it starts to dissipate energy, and it settles from an elliptical orbit into a circular orbit, and that forms an accretion disk. And from there on, you have a steady point where this accretion stream collides with the accretion disk and dissipates a lot of the energy, and that becomes a point where energy is being dissipated, so it is hotter than the rest of a disk. And we often see that glowing as a point of emission line, an emission line glow from these binaries. That is what we call the stream impact point.
Sir, so what is the dark energy?
Simple answer, I do not have a clue. So dark energy does not have anything directly to do with this talk. Dark energy was discovered about 20 years ago when we discovered that the expansion of the universe was not actually slowing down, it is accelerating. And to produce that acceleration, we need something that behaves like it has an energy density, but it has a negative pressure. And that is what we call dark energy. We independently from a cosmic microwave background infer that about 70% of the energy density of the universe is in the form of this dark energy. What it is, we still don't know. In a sense, dark energy is a name given to whatever thing we don't understand explains those observations. One idea is it is kind of an energy of empty space. It is a vacuum energy. One of its weird properties is that the energy density doesn't change as the universe expands. And so the energy density is always constant, whereas the energy density of matter decreases as the universe expands and matter becomes more diluted. The result is that over time, dark energy is becoming more and more dominant. And as the universe gets bigger, you just kind of keep creating more dark energy in empty space. Is that really what's going on? I don't know. Is it something missing in physics? Quite likely. Attempts to explain it in terms of a vacuum energy with current physics have not given anything like the right numbers. And that is about the limit of what I know about dark energy, because I'm afraid this is really not my field of research, but I do have to teach about it occasionally. But simple answer is we don't know. This is one of the biggest questions of 21st century astronomy is what is dark energy? What is most of the energy density of the universe made of? And hopefully some of you can go on and become part of figuring this out. It's an exciting field and there's a lot going on.
Yeah, thank you, sir. That is also our aim, that somebody will join later. Some of our students and the viewers who are present today will join in this research field and solve the dark energy and dark matter problem. So we have another question, and this and this may be the last question. So how much variation is happening in X-ray burst prediction with real burst, and how do you account for that error in that deviation?
Sorry, can you read that again? Do you say mass accretion?
Okay, so how much variation is happening in
Okay.
a X-ray burst prediction with real burst, and how do you account for that error in that deviation?
I'm not entirely sure that I understand the question.
Okay, I can add the question in the screen. You can see.
Hold on, I need to hide my screen. I guess I'm not sure what is meant by the error in the deviation. When we talk about X-ray bursts, we're often talking about thermonuclear X-ray bursts on neutron stars. And so that is not something that is happening here. I'm not sure if that is what is meant. In terms of what is happening in black holes, we don't really have a good idea of what is really happening. All we have is the X-rays that we can actually observe. And so we have to try and work backwards from the X-rays to try and figure out what really happened. We don't kind of have an independent measure of what the X-rays actually are. I'm sorry, you're welcome to try and expand on that question, but I may have missed the point of the question. I apologize.
Thank you, sir, for your wonderful presentation and discussion session. And we'd like to say thanks
I'm
on
sorry
the
I
behalf
did
of the
not answer my
Department of
question.
Physics. No, it's okay, sir. As the video will stay remain in Facebook and YouTube, and anybody can ask question later also, and I'll send the question to you if anybody will ask question later. So thanks
Sure.
again, sir. The main aim of our program is to motivate our student, and I think your exciting presentation and interesting topic will encourage our student. So
Good.
thanks again, and hopefully we'll arrange another webinar in the near future with you. Bye for today. Have a nice day, sir.
And you. Thank you. Bye.
Bye, sir. Bye-bye.
Okay, I don't know.